Welcome to my new calculus site. My name is John Gabriel. Today I would like to discuss one of the questions one of my subscribers asked. It is a valid question because it makes others think, well, why should we abandon the mainstream calculus if it works? But does it really work, and how does it work? Okay. So that is what I'm going to address in this video, and I am under a time limit, so I'm going to do it as quickly as I can. So let's begin. Now, this is the subscriber Cauchy, and he says, one question always puzzled me: why the hell mainstream calculus works? For example, let's say y is equal to x squared, and when we find the derivative, mainstream calculus works well. It gives you 2x, considering h very small. Well, it still doesn't give you 2x, because if h is very small, it's not 2x. It's 2x plus h, okay? So it doesn't really work. And here he says it's approximately equal to 2x. So in a sense, it works. Well, I'm sorry, Cauchy, it either works or it doesn't work. But anyway, this is a valid question which he asks, which a lot of people seem to just overlook. And I'm going to show you now why the mainstream calculus does generally work, the definition of the derivative, okay? And it works because there is such a thing as a general derivative. So what is the difference between a general derivative and a numeric derivative? Okay, so let's just pull up a screen here that I can write on, and I'll tell you. So come on. Whoops, what's happening here? That's odd. I should be able to write on this, and somehow I'm not, and that's not good. All right, there we go. Let's try that again. Okay, good. Now, I want to sketch on the screen. So, all right. So now the general derivative is usually written as f dash of x is equal to 2x, right? And obviously from this you can find the derivative at any of the points. But a numeric derivative is, say, for example, this. See? That's the derivative at a point. Now, the mainstream calculus, as you can see from our pointer here, doesn't actually find from the difference quotient the derivative at x. Okay, it doesn't find that. It finds the general derivative when you plug in 0 into h. That's why it works, okay? Because you have to plug in 0 into h to get the general derivative. And from there, you can get the rest. But you can never get, for example, the derivative at the point x is equal to 1 without first having found the general derivative. Do you understand that? Okay, so now the new calculus does all that. Okay, so for example, in the new calculus, you'll have f dash of x is equal to f of x plus n minus f of x minus m all over m plus n. And that actually works out to 2x plus n minus m. That is exactly the derivative, okay? Because this is always equal to 0 in the new calculus, all right? And so this here is both the general derivative and the derivative at a point. I don't need to do any nonsense like put a limit as h is equal to 0 there, and especially when real numbers are not defined. They don't actually exist even. They're a myth, okay? So when you do this here, you're saying, oh yeah, we're finding the limit of this finite difference quotient as h is getting close to 0. So that is really the main reason why you should turn to the new calculus, okay? So the new calculus defines a derivative in terms of the mean value theorem. And it uses the slope of a parallel secant line to the tangent line, okay? So it doesn't matter where you are. The new calculus will always give you the correct general and numeric derivative. But Newton's bogus calculus doesn't do that. It will just give you the general derivative, and you have to do something really stupid to get it. You have to set h is equal to 0, because 2x plus h is not the derivative. And h can never be infinitesimal, because infinitesimal is a junk concept. Think about it. To have an infinitesimal, you must believe in infinity, okay? Because an infinitesimal, strictly speaking, is 1 divided by infinity. But infinity is not a number, you morons. I'm not being angry at Cauchy, by the way. So this, Cauchy, please don't take this personally, but it's directed to all the morons out there. You have to think about these concepts very clearly. Do you want to continue using your bogus mainstream calculus, which does have a lot of errors in it and doesn't even have the correct definition of a tangent line or a derivative or an integral, but you continue to use it and you have to learn all that machinery? For example, you can't really even understand the definition in your mainstream calculus of the derivative unless you do at least a 6-month introduction course to limit theory, okay? You have to know and understand what the hell convergence means, okay? What is convergence all about? You have to learn about the least upper bound theorems and all those things, okay? Whereas the new calculus doesn't concern itself with that theory. It tells you, it gives you all these definitions in terms of analytic geometry. In other words, a high school student can learn that. Now, what's better than that? I can't understand why on earth anyone would want to torture a student with all that bullshit about limits and nonsense about continuity and things which mainstream academics do not understand. In general, the majority of them have never understood calculus, don't know why it works, don't even understand that the fundamental theorem of calculus is the mean value theorem, okay? Every other theorem is derived directly from the mean value theorem. The reason you can calculate the area under a curve, or the volume, or the hypervolume, is that you have a telescoping sum, which is what comes out of the mean value theorem when you attempt to find the arithmetic mean of quote unquote infinitely many y-ordinate lengths. Do you get that? You'd never be able to do that in practice because the super task is impossible, okay? So it turns out that, excuse me, that sum actually telescopes, and it turns out to be the boundaries in, let's say, a planar region, or if you're looking at Green's theorem, it's a little more involved in that, but it's still the boundary of the region that you're looking at, regardless of what it is, whether it's in a hypervolume or a planar region or just a plain volume, okay? So that's the beauty of the mean value theorem. It allows us to do something that is seemingly impossible, but we're doing it in a finite number of steps. And that's the same thing with the new calculus integral. So if you look at one of my previous videos here, I actually explain those things to you. I show you that you can calculate an integral in a finite number of steps provided it has an antiderivative. Okay? So let's just look at these videos here. I'll show you which one that is. And so the videos you should look at are deriving arc length using the new calculus. In this video, I show you the new calculus definition of integral. And it doesn't matter what you're summing from. You know, it can be k is equal to 1 or k is equal to 2. You'll always get the correct arc length, whichever one of those you use. That is the significance of what I'm telling you in this video here. Yes? You've never seen that in your bogus calculus because no one has ever understood calculus as well as I do. Not Archimedes, not Newton, not Leibniz, not those morons, Cauchy and Weierstrass and all the other idiots who came before me. I am the master of calculus, okay? And in fact, I'd go as far as saying that nobody has ever understood number or arithmetic mean or in mathematics in general as well as I do. I have a very deep understanding because I chose not to accept what was told to me, but to question it and to think about it. And if you want to become a good mathematician, like I am, you need to question things, okay? You can't just be told this is a theorem and this is a definition, use it. You're not even compelled to accept a definition that doesn't make sense, because ill-formed concepts inevitably lead to more ill-formed concepts, contradictions, paradoxes, and theory that eventually becomes so massive it's unusable. Not only is it unusable, but it takes a lifetime to learn, and generally, if anything else is noticed, it's usually not even worth all the time and effort, because, I mean, take a subject like topology. Many math graduates take that for their dissertation. It's such a load of rot. I mean, there's almost absolutely nothing that you can do with it. They take a previous dissertation, and I've read many of them, and they simply notice something else that's new and they modify it. It's like a plagiarized new dissertation, and that's how they get their PhD, which is just a piece of crap if you ask me. Okay, and I've read many of them, and there are professors, by the way, who agree with me, mainstream professors. So anyhow, that's all I wanted to talk about in this video, to give you a general idea of the mainstream derivative and why you generally get the correct results, but the theory is flawed. Okay, the theory is flawed. My name is John Gabriel. This is a new calculus channel. Till next time, goodbye.